Thanks a lot. It's very nice to be here. Thank you for inviting me. Um, so this topic has really seen rapid development in the last couple of years. Um, and so preparing this review talk was a useful exercise for me to try to keep up with all of those rapid developments. I think that many people in the audience know a lot more about some aspects of this than I do. So please feel free to chime in with comments or questions. Um, and This review talk will be from my own kind of perspective, and I don't have a complete view of everything, so I'm happy to get input from everyone. Um, okay, so my entrance into thinking about the conformal bootstrap at finite temperature was based on a kind of dream um, of of how we should try to define QFT or CFT. Um, so when I was in graduate school, I learned about what I still feel is one of the most beautiful definitions of QFT, which is the definition based on something like the Atiyah-Segal axioms. So the idea of these axioms is that a quantum field theory is a functor from a Bordism category to some category of Hilbert spaces. Um, and uh, Said if we unpack that a little bit, it means that a QFT is, here I'm calling my QFT Z. So a QFT can associate to a manifold maps between Hilbert spaces. If you have a manifold with two boundaries, n and n prime, then Z of this manifold is a linear map from the Hilbert spaces associated to n and n prime. And these linear maps under composition correspond to gluing of manifolds. So this functor Z has to satisfy cutting and gluing axioms that look kind of like this. And this is a very beautiful axiomatization of what we mean by what we might mean by a path integral. Even in the context where we don't have a Lagrangian description, a path integral has to have some locality properties, and those locality properties are captured by cutting and gluing, at least in Euclidean signature. So this is a very beautiful picture of what a QFT is or what it should be. And it's been made very concrete in some examples. Maybe the classic example that you first learn about is topological quantum field theory in 2 dimensions, where you can take this mathematical definition and flesh it out completely, and you find that 2D TQFTs are equivalent to Frobenius algebras. But this point of view is also at the core of Witten's solution to Chern-Simons theory. And there are now many other examples of at least TQFTs that can be treated in this way. But as far as I know, there aren't very many examples where we have a non-topological theory where we can present the theory in terms of this data. I guess the one exception is 2D CFT, which I'll mention in a second. So this is one possible definition of what a QFT can be. But in flat space, at least in the case of CFT, we have another possible definition, which is that a CFT in flat space should be a solution to the bootstrap equations. One of the things that we've learned since the renaissance of the conformal bootstrap is that the space of solutions to these equations, even in higher dimensions, has a lot of structure. It's possible that it's discrete. It's likely that it's discrete. And this is a reasonable way to try to define what you mean by a CFT in flat space. And not only is it reasonable, but the numerical bootstrap tells us that it's computationally effective. We don't know exactly how computationally effective, but basically you can start with some finite amount of information, and you can use these equations in a practical way to get new numerical information. Can we bring these definitions together? So can we give a more complete definition of what we mean by a CFT? And in the spirit of a TSE goal, that means that we should be able to compute CFT partition functions on non-trivial manifolds. And that should be additional data of the CFT. And the paradigmatic example for this is in 2D CFT, where we do have a full definition. We do have a full Atiyah-Siegel-like definition of a 2D CFT. We know that it's a solution to the flat space crossing equations, and also an additional type of crossing equation coming from modular invariance of one-point functions on the torus. And that includes, of course, modular invariance of the torus partition function. So Moore and Seiberg showed that if you have a solution to all of these conditions, then it has consistent correlation functions and partition functions on any Riemann surface, and so you have a complete presentation of what we should think of as a local QFT, local CFT. So what about in higher dimensions? So in higher dimensions, there are many questions, and we don't really have very many answers. So, of course, we want to be able to compute partition functions and correlation functions on other manifolds. You could ask what kinds of manifolds you're allowed to put the theory on, and that's an interesting question. But maybe at a minimum, we should ask that we can put the theory on flat manifolds or conformally flat manifolds. And then we can worry about coupling to non-trivial curvature later. And so one example might be a torus, a d-dimensional torus. So can we compute partition functions and correlation functions of CFTs on a d-dimensional torus? And this particular example is important also because it's what Monte Carlo simulations compute typically. So it would be great if we could make predictions for CFT correlators on the torus. Then we could compare to Monte Carlo, and there could be lots of interesting things to do there. I guess one recent numerical technique that's been gaining a lot of steam is the fuzzy sphere method, which is a regularization for a Hamiltonian model that respects the symmetries of the sphere. Maybe there's also a fuzzy torus. Maybe you could do the same thing on the fuzzy torus. I'm not sure, so it's just a random comment. So anyway, this is an important example. We'd like to understand this example. And there are certainly modular invariance constraints for torus one-point functions that you can write down. And we don't know whether this data is additional data that we need to add to the CFT. It satisfies some consistency with the bulk OPE data, but is it determined by the bulk OPE data or what? We don't really know. From this perspective, the thermal bootstrap is kind of an intermediate example. It's sort of like the simplest example of trying to understand data on another manifold that's not conformally equivalent to flat space. So why is it nice? Well, it's flat and it has a lot of symmetries. And because it's flat, we can compute correlators using the OPE. So if we have an endpoint function on S1 cross R d minus 1, then we can use the OPE recursively to reduce it to an n minus 1 point function and so on. And eventually we get down to 1-point functions. And the new ingredient at finite temperature is that 1-point functions are non-trivial. Now, there's a sort of a question of, what the new data of the theory is, from the perspective of the bootstrap. Do we need to add new data or that satisfies consistency conditions, or is there no new information? And in the thermal case, these thermal 1-point functions are in principle just determined by the flat space data. So you might say, well, this example is kind of boring because I just need to solve the conformal bootstrap in flat space, and then I will have solved the thermal bootstrap as well. But the problem is that this formula that I wrote here for the thermal one-point functions in terms of one-point functions on SD minus 1 cross S1 is practically very hard to use, let's say in a situation where you haven't completely solved the theory. Because it requires taking a limit, it requires knowing asymptotics of CFT data a priori, and that can be very hard. So instead, we can ask, well, in the spirit of the numerical bootstrap, can we constrain this thermal data with a finite amount of input? Just like in the numerical bootstrap for flat space 4-point functions, we can put in a finite amount of information and get constraints on observables. Can we do the same thing in this case? So can we maybe pretend that the thermal 1-point functions are new data, even though in principle they're not, and write down consistency conditions and solve them. So that's one motivation for thinking about the thermal bootstrap. Of course, there are many others, but this is one direction, and this is the direction that sort of got me interested in this problem in the first place. Any questions? Okay. So so good. So what are the consistency conditions on these thermal 1-point functions? So there's a natural idea, which is to look at thermal 2-point functions, which connect this extra 1-point data with flat space OPE data. And again, for 2-point functions, we can reduce them to 1-point functions using the OPE. So geometrically, we can start with a pair of operators at 2 different points. Let's say, so we have phi at x1 and phi at x2 inside S1 with some length beta times RD minus 1. Because this space is flat, as long as the phi's are sufficiently close together, we can surround them with a ball. And then from the perspective of the ball, inside the ball, it looks just like flat space, and you can't tell that you're at finite temperature. So we can write down an inequality in radial quantization that says that the state on the surface of the ball created by these 2 phi insertions is equivalent to a sum of local operator insertions at the middle. And so we basically replace this ball with 2 phi's with a ball with a single O inside and a sum over O's. With a contribution from flat space 3-point functions. And so this reduces the 2-point function to a sum of 1-point functions. And then the 1-point functions at finite temperature are highly constrained by symmetry. So the 1-point function at finite temperature has to satisfy lower dimensional rotational invariance and translation invariance and dimensional analysis. And that constrains it to be some constant B sub O, so this thermal 1-point coefficient, which is theory dependent, times some universal kinematic factors. There's a tensor, which is just built out of the unit vector in the time direction, and a power of beta that's determined by dimensional analysis. And this is independent of x because thermal flat space is translation invariant. So plugging this in, you get a formula for the thermal 2-point function as a sum over operators times these universal factors. So the key one to pay attention to is really this one, powers of the separation between the 2 operators that depend on the dimension of the operator in their OPE. So there was an observation by Elshok and Papadodimas back in 2011 that this formula for the thermal 2-point function does not manifestly obey periodicity around the thermal circle, which is the KMS condition. And this leads to a kind of crossing equation. So if I call this correlator G of x comma tau, then this G has to satisfy this consistency equation, which is not satisfied term by term in this sum. And because it's not satisfied term by term, we get a non-trivial equation that relates all of the coefficients to each other in the same spirit as crossing equations for 4-point functions. So it leads to a natural question: can we constrain the B sub O's, the thermal 1-point functions, using this equation? An immediate issue is that the coefficients in this equation, B sub O times F phi phi O, are not sign definite. So we can't immediately apply the machinery of the numerical bootstrap to this equation because we don't have the inequalities that we need to make the bootstrap machine work. And the same issue also appears in the boundary in the defect bootstrap, and where you have correlators in the presence of defects or correlators in the presence of boundaries, and those correlators end up depending on products of bulk data and defect data that are not sign definite. And so you get the same problems. And so many of the issues and questions about the thermal bootstrap have very precise analogs for the boundary bootstrap and defect bootstrap. So most of the things that I talk about will have in this talk will probably have boundary slash defect analogs that may or may not have been explored yet. There are a few different directions that one could try to go with this equation. And I'll try to describe a little bit about what has been done in the last few years. And again, there's been a huge explosion of work on this, at least huge by some standards. What can one do? So one approach that has not worked, but
Actually, sorry, can I
yeah.
just ask you a quick question? In this expression for the 2-point function, uh, is there any signature of conformal invariance or just scale invariance?
Good question. So uh, let's see. Um, hmm. I think it's just scale invariance. So I think you would have the same. I think you would have the same equation in a scale invariant theory. Um, I guess the only thing conformal invariance buys you is that this sum here is only over primaries because descendants have vanishing 1-point functions.
But I guess that would be, I guess there's no descendant operator in a scale invariant theory. So
Yeah,
anyway, so
that's right. That's right. So it just means that you should expect the sum to be sparser in a CFT,
mm,
some sparser
mm,
sense.
mhm. Is there some word identity or something maybe that could be useful? I don't know. Yeah.
Yeah. So the good. So how do you use word identities here? So you can usually when you want to derive a word identity for a correlator, you would start with the operators in the correlator, and then you surround them with a topological surface operator implementing the symmetry. And then if you're in flat space, you can do two things. You can take the topological surface and you can shrink it down so that it surrounds each operator individually. And that gives you some differential operators acting on the operators. Or you can expand it out to infinity, where uh, where it contributes 0 if you have conformally invariant boundary conditions. And that gives you an equation that 0 is equal to some contribution from each individual operator. If you try to do this at finite temperature, then you have some periodic boundary conditions. And what happens is that for the conformal killing vectors that are not globally defined on S1 cross RD minus 1, when you try to bring this topological surface up here, and it goes it goes all the way up here, and you bring the topological surface down here, it goes all the way down here, and then you might want them to collide and cancel with each other around the thermal circle, and that does not happen if the killing vector is not globally defined. So I don't know how to derive a ward affinity using, say, special conformal generators in this geometry. Does that answer your question?
Yeah, thanks. That's interesting. Yeah.
Okay, great. Okay, so what can one do? So first, I'm going to talk about an approach that has not worked yet, but I still feel that it's interesting to think about, and maybe something can be made out of it. And then I'll mention the things that people have been doing and actually making progress on. So there's this idea of completing the square. So this is how we deal with non-sign definiteness in the bootstrap for 4-point functions. So in that case, there's an analogous question. Let's say suppose we start with a correlator of 2 sigmas and 2 epsilons in the Ising model. That has a conformal block expansion that also contains non-sign definite terms, the product of F sigma sigma O with F epsilon epsilon O. And we don't know the signs of these individual OP coefficients, so we don't know the sign of this product. So the way to deal with this is to look at not just one correlator, but a system of correlators, and we can arrange them into a matrix. So we can form this 2x2 matrix of correlators, and then this matrix of correlators, when expressed in terms of conformal blocks, you end up with a sum of matrices of 3-point coefficients. And the problematic one is an off-diagonal term in this matrix. And the nice thing is that the full matrix is positive semi-definite. This non-sign definite part was just an off-diagonal term. And then you can run the bootstrap machinery using these positive semi-definite matrices and get interesting constraints. So it's natural to ask if we can do this for the thermal bootstrap. And so to see what that should look like, we can start by looking at our thermal 2-point function. And we can think of it as a kind of contraction of the 4-point function. So we could start with a 4-point function, which would be this thing in the box here. And then we just pair up 2 of the external legs and sum over them. So this circle here stands for a sum over operators O prime with effectively a high temperature limit for that sum of operators. So that's what my notation, circle notation, means here. If we apply crossing to this 4-point function in the box, then we get the thing on the right-hand side. And that would be a different expression for the thermal 2-point function. What is this expression concretely? Well, it expresses the 2-point function as a sum over 2 types of states. We have a state alpha here that's propagating on this leg, and then another state alpha prime propagating on this other leg, and then phi insertions between them. And this is the spectral decomposition of the thermal 2-point function. So we think of states where we quantize the theory using RD-1 as our spatial slice. And then we have a state on RD-1. We act with phi to get a new state, and then we act with phi again to go back to the original state. And then we have periodicity. And so this is the spectral decomposition. And one thing about the spectral decomposition is it manifests KMS. So this equality between these 2 things is actually a stronger version of the KMS condition on the thermal 2-point function. It implies the KMS condition, but it also potentially implies more information than just that. So good. So we've sort of embedded our thermal bootstrap equation in this framework. And then the idea is to think of this part of the diagram as some kind of off-diagonal term in a matrix of pairings between things. So on the left here, we have a pairing between this bulk 3-point vertex and this funny circle. So we should also consider a pairing between two bulk 3-point vertices. And that satisfies a crossing equation, and that's just the crossing equation for 4-point functions on flat space. So one of the diagonal terms in the matrix that we're building is just the 4-point crossing equation, which is great. And this, of course, has f phi o squared in it, which is sign definite. The other diagonal term would come from taking a pairing between two circles. So we have a pair of circles here and here, and we take the inner product between them. And then this should be equal to something like this. So if we construct this thing, it's going to be some kind of sum that has squares of thermal 1-point functions in it. So some kind of sum over O of squares of thermal 1-point functions times kinematic things. And what about the right-hand side? Well, it's a little bit harder to characterize what this is, but this picture was the motivation for a recent paper that I wrote with my student Yushin Zhu. And the geometric picture here is the left-hand side of this. Well, you're studying the partition function of the CFT on a funny geometry. That geometry is two copies of thermal flat space. So we have one copy here and another copy here. And then from each copy, you drill out a ball, and then you connect those the boundaries of those balls with a cylinder. And this picture here, that in this very schematic sort of graph notation, corresponds to taking this geometry and slicing it in two different ways. So one way to slice it is you cut it into two halves, left and right, and that leads to this sum over operators of thermal 1-point functions squared. And then the other way of slicing it is you kind of slice it through horizontally, like that. You find a horizontal plane and you cut it through. And so you might look for some crossing equation that relates this sum of thermal 1-point functions squared to whatever on earth this inner product is. I might say more about this later. We explored this idea a little bit and we didn't manage to get it to work. But I still think that this function of the sum of thermal 1-point functions squared is a very interesting object. I hope we can learn more about it, and maybe it will become useful in the thermal bootstrap. So, okay, so what have people actually made progress with? So one technique has essentially been to try to exploit sparsity. So the very basic version of this technique is to take the thermal 2-point function and let's just pretend that we can approximate it with a finite sum of operators. We truncate it to a finite sum, and then the KMS condition. So now there are a finite number of undetermined terms. The KMS condition is an infinite number of equations. So we can try to approximately solve the KMS equation in terms of that finite number of terms and get approximations for the 1-point functions. And this is sort of in the spirit of Gliozzi. So Gliozzi did basically something like this for the 4-point function in flat space. And so there's a question of whether you can do this. This is very hard to make work. And in general, this is a hard road to go down. But people have come up with various improvements, some of which are pretty ingenious and seem to work well. So instead of just doing this harsh truncation, a better idea is to try to account somehow for the terms that you dropped. And the thing that I did with these collaborators back in 2018 was essentially try to apply this idea at large J. So use somehow determine the asymptotics of the CFT 2-point function at large J. And for this, there's a dispersion relation that helps. And then that lets you parameterize the large spin contributions to the thermal 2-point function so that you don't have to just do a harsh truncation in everything. You can truncate in delta, but then include large spins. In the end, you try to write down an ansatz for the two-point function in terms of a finite number of parameters and then solve the KMS equation. A better approach, so the problem with that is you're still truncating in delta, and the high delta terms that you drop might be important. So a better approach, and one that seems to work quite well in practice, is to do a better job of modeling the large delta contributions. So for example, you can try to solve for the behavior at large delta analytically, and then put that into your ansatz, and then solve solve for the unknowns in your ansatz like that. And and this seems to work very well, at least for correlators of low dimension operators in the Ising model and the ON models. A related idea is this ansatz in terms of a sum of GFF correlators. And here's an example of the kind of results that people, many of whom are in the audience, have been able to get with these techniques. So it's a plot of the thermal two-point function of sigma at zero spatial separation. So you can see that there are these two singularities at 0 and, well, I guess tau probably, it says it runs from 0 to 40. I think that's probably related to the Monte Carlo simulation. So it was done on a lattice where the tau size was 40. But so this is the OPE singularity here, and this is the image of the OPE singularity around the thermal circle. And you can see a comparison between the analytic result that's obtained by starting with an ansatz with a finite number of parameters and then approximately solving KMS for these parameters, and the Monte Carlo result. And it's very good. And recently there's another approach to this kind of problem where instead of modeling the large delta behavior in terms of series in 1 over delta that's computed using KMS analytically, you can try to model it using other kinds of functions. So they were interested in using neural networks to model the large delta behavior, and they also have some nice results from that. I think it's important to ask here in these methods, what is the input and what is the output? Because there's something a little bit circular seeming about this process that I think we should try to think about and address, and probably many of you have thought about. So it's a bit funny. So we start with the KMS condition, and we use the KMS condition to solve for large J behavior. And then we also use the KMS condition to solve for a large delta behavior. And then we plug all of that back in to try to solve the KMS condition. So where exactly have we constrained the theory? And I think my understanding is that the main constraint is really coming from some assumption about the sparsity of the low-lying spectrum. So if you allow arbitrary operators with arbitrary dimensions to appear in this sum, you have a sum with no sign definiteness properties. So it's not obvious to me that there's really any information there. The idea that's being explored in these methods is that, well, if we're still going to allow an infinite number of terms, but we're going to disallow terms in a certain range of deltas. And the hope is that that disallowing of terms in a certain range of deltas will give constraints. I think it would be nice to understand this a little better, exactly what the input is. And I think one thing that concerns me about extending this to more correlators and bigger systems of correlators is that if we think about higher dimension operators, phi, so if phi instead of being sigma, it's the epsilon prime operator in the 3D DESY model, which has dimension 3.8, or maybe it's the lowest dimension parity odd scalar in the 3D DESY model, which has dimension 11. The problem there is that the higher dimension operators are likely to have larger OP coefficients with other high dimension operators. And furthermore, the contributions in the OPE, which look like this, get harder to distinguish when delta phi is bigger. Because when delta phi is big, all of the terms look like big, sort of decaying things. And it's harder to see the differences between different deltas. So it looks to me like sparsity of the low-lying spectrum is going to become a losing battle if we try to extend these methods to more correlators. And that we really need additional information than this sparsity. That would be my guess. It's vague and not rigorous. And I would love if someone could either teach me otherwise or make these things more precise. But yeah, I think that this approach seems to work great for these special correlators in the Ising and Owen models. It would be really nice to extend it, and we may need new ideas to do that. So another approach that is to think about holographic theories, where again we have a lot of constraints on the form of the two-point function, and this area has really exploded. I'm not going to say much about it because I noticed the list of future thermal seminars, and I think there are at least a couple speakers coming up soon about this. So I'll just advertise some of the things that have been going on in this area and encourage you to come to future thermal seminars or watch them on YouTube. So in holography, the main constraint is one of the important constraints is that this thermal two-point function basically gets two kinds of contributions, one from double trace operators and another from multi-traces of the stress tensor. These two pieces have been explored intensively in the last several years. One of the interesting things about them is that these pieces individually exhibit singularities at a special value of tau. And the bulk interpretation of these singularities is that they're related to null geodesics that bounce off of the black hole singularity. This null geodesic picture, I think, has been known for a while. I should actually have the references. I should have written them in my slides, but I didn't. But I think I have them in my notes. So there are papers by Fidkowski, Hubany, Klavan, and Shanker from 2003, and Miscioscia and Liu in 2005, pointing out the presence of these kinds of features in the thermal two-point function and its relation to the black hole singularity. But one of the explosions in recent times has been an understanding of how to calculate these things more effectively using bulk methods and also understanding the relationship to the OPE. So that's a very interesting topic. I encourage you to look at future thermal seminars for that. I guess I'll just mention, I think one of the really big questions here is, can we predict this thermal data in holographic theories using just the boundary theory? That's one of the big questions. And it's a really big question. So all of these calculations, maybe I shouldn't say all of them, I think most of these calculations, really they're using the bulk. They're doing bulk computations. Maybe they use CFT techniques to help organize the bulk computations, but in the end, it's a bulk computation. So the question is, can we just use the boundary? And this question is big because it's sort of at the heart of the ADS-CFT correspondence. So there's one version of the ADS-CFT correspondence where you just ask about flat space endpoint functions. Do flat space endpoint functions of the CFT have to agree with sums of Witten diagrams in ADS? So and that version of the of deriving ADS-CFT, that was sort of proposed by HPPS, Heemskerk, Polchinski, Penedonis, and Sully, where they asked the question, can you predict these endpoint correlators using just boundary methods and find that they have to agree with a theory of quantum gravity in ADS? But ADS-CFT implies that much more should agree between the bulk and the boundary, and these thermal correlators are an important example. So in terms of flat space endpoint functions, there's been a lot of progress on this question, this HPPS question. And it's understood at least how to answer this question for 3 and 4-point functions. It hasn't been understood how to do this for higher point functions. But maybe those technical things can be overcome. But then if you wanted to like turn this into a proof of ADS-CFT, so the thing we're imagining is you want to say something like, suppose you have a CFT with a large central charge and a large gap in the single trace spectrum. Can you prove that all of its observables agree with Einstein gravity plus small corrections? That would be a kind of proof of ADS-CFT, a bootstrappy proof of ADS-CFT. So the thermal correlators are sort of the next step after the flat space correlators in establishing that program. I don't know whether that program will be successful, but this is a dream that we should have, that we should be able to we want to prove ADS-CFT in this way. So I think it's interesting to ask whether there are any lessons that we can draw from the progress that has been made for flat space endpoint functions. Can we use anything from this to try to help us with predicting thermal data from just the boundary? And I guess one lesson, I don't know whether it's useful, is that in the case of flat space endpoint functions, the constraints were really first understood in the bulk. So they were constraints coming from causality. People were thinking about gravitational theories in flat space, and there are questions like, can you build a time machine? And you can show that your ability to build a time machine is related to the size of higher derivative terms in the effective action for gravity. There's a condition called commutativity of shocks, where if you impose this condition, it singles out Einstein gravity. And then these two observations that there shouldn't be time machines and that shocks should commute, they can be combined essentially into a set of dispersion relations for flat space amplitudes for gravitons. So all of this is just in flat space, thinking about gravity theories in flat space. The translation to CFT, once the story was understood in flat space, the translation to CFT was, it followed pretty soon after. So I guess the lesson, it's a very vague lesson, is to think about causality in the bulk and really try to understand bulk causality as well as we possibly can before worrying about phrasing it in terms of the CFT. And the hope is that if we find the right formulation of constraints from bulk causality, then the formulation in CFT will be forthcoming. So that's a very vague comment about this. Okay, any questions about that? All right, so the last topic I wanted to mention is uh, is relations between the bootstrap and effective field theories, in particular effective field theories for finite temperature. So there was an observation made several years ago by these groups that long distance correlators and long distance partition functions, by which I mean partition functions where the curvature scale is very long, they are controlled by a kind of classical effective action. Um, and this classical effective action has to satisfy various consistency conditions. And this actually puts strong constraints on certain thermal data. Um, so the simplest version of this is for equilibrium correlators. And the idea is to think about a CFT at finite temperature and couple it to a background metric. And we should think of this background metric as being like the metric for S1 cross RD minus 1, but with wiggles. So a wiggly S1 cross RD minus 1. Um, and uh, um, so one way of thinking about this is to dimensionally reduce the theory on the circle. And generically, if you start with a CFT and you dimensionally reduce on a circle, generically you'll get a massive theory in one lower dimension. And so if the CFT is coupled to some background metric, and we give this background metric the Kaluza-Klein form, so that in particular it has a circle isometry, then the partition function of the CFT should be the same as the partition function of some kind of massive theory coupled to these background fields. And the nice thing about a massive theory is that correlations die at long distances, and therefore its partition function, all its correlators can be approximated basically in terms of delta functions and their derivatives, right? You have correlators that have some structure. Let's say there's like a singularity when 2 points get close, but they die exponentially. So if you zoom out really, really far, that just looks like a delta function and maybe some series of derivatives of delta functions. And so what that means in terms of the partition function is that it can be approximated in terms of a classical action of the background fields, e to the minus s thermal. And the claim is that this one classical action controls all of the sort of long distance wiggly behavior of the thermal theory. And so one thing that I should mention, because it's also an interesting recent development, is it is expected that the theory at finite temperature, when you reduce on the circle, is gapped. And for a while, there was lore that it should be trivially gapped. It should have like a unique vacuum. But recently, it was found that you can actually have spontaneous symmetry breaking at finite temperature in CFT. So these people, Komargovsky and Popov, actually found explicit examples where there's spontaneous symmetry breaking at finite temperature. And in those examples, that would mean that this S thermal would be a function not just of these background fields, but it would also have a discrete scalar field as well. So you could have additional discrete, basically TQFT-like degrees of freedom if you don't have a trivially gapped theory at finite temperature. So it's an interesting case to think about. But anyway, so there's this classical action that controls the partition function at finite temperature. And this makes some predictions for CFT that I don't know how to get in any other ways. So an example is you can look at the partition function on S1 cross SD minus 1 at high temperature. It's controlled by this effective action, and that makes a prediction that it should go like e to the minus s thermal, and minus s thermal in this case looks like this, plus corrections. I forgot to write the corrections. Plus dot dot dot. But this would be the leading term at small beta. And at the same time, this partition function is the sum over operators of the theory of e to the minus beta times delta. And so you can use this to, you can inverse Laplace transform this to get the density of states of the theory. And this makes a prediction, for example, in a 3D CFT that the density of states looks like this. And that's kind of a generalization of the Carty formula to higher dimensional CFTs. And this coefficient F here actually appeared previously in the talk, though I didn't mention it. It's essentially the thermal one-point function of the stress tensor. And it's also the free energy density of the CFT. So I think this is pretty interesting. I like the chain of information here. I feel one thing I like about this is that there is new information beyond the bootstrap. At least it seems like it's beyond the bootstrap, but physics information that you're injecting to get something out here, namely the locality of the theory at finite temperature. So the fact that the theory is massive and therefore can be described in terms of this local action really makes a lot of predictions for the structure of the theory. It's not obvious that this is captured by the bootstrap axioms in any clear way, but it's physically very intuitive. So I like that. It's a new physics input, and so we can maybe get new things out of it. In a paper a few years ago, we tried to take this idea of an effective action for the theory reduced on S1 and see if it could be applied in more general situations. And there's this hotspot idea where you could have some general manifold that's very complicated, but let's suppose that somewhere in the manifold, it develops a location where there's a very tiny circle. So right down here, some tiny circle, tiny S1. Then near that location, it looks a lot like a thermal theory. And furthermore, if you take the thermal effective action and you try to compute its contribution from that location, you find that it's really big. So if you look back here at this formula, you can see it looks like e to the something that's getting huge when beta is getting small. So there's some very large contribution to the log of the partition function from this region. In other regions of the manifold, it's hard to imagine how they could produce a similarly huge contribution because nothing interesting is happening to the geometry in those other regions when this circle is shrinking. So that's the idea. The idea essentially is that singularities in log z that come from small circles can be computed using S-thermal. And this promotes S-thermal to a much more a much more general tool because you can try to find these kinds of locations on many different kinds of manifolds. They don't just have to be a global circle fibration. And so we applied this idea to one of the manifolds that appeared earlier in the talk, the one that encodes squares of conformal three-point functions. So there the idea is you start with two copies of SD and you drill out 3 balls from each copy and you connect them with cylinders. And this is actually this manifold is this is a representation as a manifold of this graph that appeared early in the talk, where you have 2 3-point functions like this and you connect them like that. If you take these cylinders and you imagine making them short, then there's a kind of hotspot that develops. There are hotspots that develop. I'll draw them again in a different color because I've been using too much red. So when the cylinders get short, there's a hotspot that develops where you go from one cylinder to the other, and then down one cylinder, across, and down back up the other cylinder. And so there's this effective effective inverse temperature that you can write down, which looks like this. and that makes a prediction that the partition function of this manifold has a singularity that is of this form, e to the f times volume of sd minus 1 over beta effective to the d minus 1. And then there could be contributions from other hotspots. And you can then use this in the same way that Julien used the formula up here to invert and make predictions for asymptotics of CFT data. So the idea is to take the sum of take the sum of flat space 3-point functions squared and invert it, apply that inversion to this formula with the singularities predicted by the thermal effective action, and then makes predictions for F123 squared at large, delta 1, delta 2, and delta 3. These are predictions for general CFTs. There are special techniques in 2D that you can use to make predictions for large dimension 3-point functions in 2D. This in general is for general CFT. So this idea essentially of finding singularities in partition functions and inverting them to learn about CFT asymptotics, that there's been some other recent work on that I should mention. So one interesting one is this work by these authors, where they were thinking about Lorentzian partition functions. So going beyond just Euclidean partition functions, and they were interested in looking at observables where you basically turn on a large angular velocity. So looking at something like trace of e to the minus beta times d minus omega j, where d is delta. I guess I should call it delta. Delta minus omega j. So little omega here has an interpretation in hydrodynamics as being like the angular velocity of a spinning fluid of CFT, and omega goes to 1 is when it's spinning at the speed of light. And the claim is that this partition function looks like e to the some function of beta. Oops. Uh-oh. Sorry about that. Put this back up here. Some function of beta divided by 1 minus omega squared. The one way of interpreting this result is that you can think of it kind of as like a hotspot type thing, but it's a new kind of hotspot. It's a Lorentzian hotspot. What happens is that as omega goes to 1, the geometry, actually, let me back up a second and go back to this kind of hotspot. So I described these hotspots in terms of tiny circles. But one of the key things here that you can do is you can change your Weyl frame. And instead of thinking of it as a circle that's becoming tiny, you can think of it as a large region of thermal flat space that's opening up inside the manifold. So you can think of it in terms of shrinking circles, but you can also think of it in terms of growing pancakes. So you think of thermal flat space as like a pancake, and it's getting bigger and bigger and bigger. And this large contribution is coming from the volume of this large growing region. So there's a very similar thing in this Lorentzian situation, where they find that as omega goes to 1, there's essentially an emergent h d minus 1 cross S1. So in the case of the first kind of hotspot that I described, there was an emergent r d minus 1 cross S1. And so this emergent RD-1 cross S1 gives this very large contribution, which looks like the volume of RD-1, um, uh, where we should think of this as being like 1 over beta effective to the D-1. Um, so in the Lorentzian case, you have an emergent HD-1, and that's why you get a contribution from the volume, but that contribution is temperature dependent because HD-1 cross S1, the partition function on that space depends non-trivially on beta because H has some dimensionful curvature. But it's a very, very related, it's a very, very similar thing. And I think that it leads to interesting questions, like, can we find other manifolds with this emergent hyperbolic space? And maybe that thinking about different types of manifolds, partition functions of different manifolds in Lorentzian signature, so taking these kinds of limits of large angular velocity could open up these hyperbolic spaces, and we could have other universal formulas for singularities of those Lorentzian or partially Lorentzian manifolds. So I think that's interesting to think about. It's hard to visualize what some of these manifolds would look like if we start analytically continuing the moduli to go into Lorentzian signature, but I think it's very interesting. And let's see, there's been other work on CFT asymptotics. So there's this older work by Luca Della Cortese where he was talking about the relationship of hydrodynamics and how hydrodynamics can make predictions for heavy prime light 3-point functions. The idea being that the light operator can create a transition from one state to another, from a hydrodynamic state to another, and that in terms of CFT data is one heavy operator to a different nearby heavy operator. And so hydrodynamics provides the effective field theory. That's the extra physics input. And then from that, you can deduce things about CFT data that is not obviously present in the bootstrap axioms. And then there was also recent work on 1-point functions on SD-1 cross S1, applying similar ideas. So I think this is I like these directions because I don't know of any other ways to access this data. I think it would be great if we could find other ways to compute this data, in particular to do checks. For example, even in a free theory, I don't know what the partition function is on some of these funny manifolds. And it would be nice if we could compute that either by explicitly enumerating operators or by computing partition functions directly. It seems like there's a lot to learn about these types of observables and really a lot to do. Another thing that I would really love about this subject is if we could somehow get away from asymptotics to sharp statements, sharp bounds. Everything here has a squiggly line, and I don't like squiggly lines. So a challenge is to determine what the numerical coefficients are in front of all of these equations and come up with rigorous error terms. Okay, so that's it. That's all I wanted to talk about. So I'll end there.